I understand this is roughly an hour talk. Slides probably won't even take that long, so encourage any questions along the way or afterwards or whatever. Not in a hurry. Yes, this is joint work with Giacomo Lanzani and Philip Strack, and our motivation is that people not only have imperfect memory, you don't remember everything, but it's selective. So you're more likely to remember some things than others. And there's various examples of this that have been observed in psychology literature. Positive memory bias, you tend to remember good things and suppress bad experiences. Cognitive dissonance reduction, don't remember things that don't fit your worldview. Associativeness, which I'll explain a bit later on. Confirmatory bias. And we're going to study the implications of these biases in a dynamic model where it's a myopic agent that picks actions that maximize their expected utility, their myopic utility, but of course their actions influence what they see, which will influence what they do next. So our question is, what beliefs will the agent develop? How will they behave? And how will selective memory distort the limit behavior? And our answer to that question is this concept of selective memory equilibrium that we show describes the long-run behavior of an agent with selective memory. So before we get to the model formally, let's just try an example. There's an agent who's going to repeatedly observe the outcome of a test. So they can pass it, outcome y equals 1, or fail it, outcome y equals 0. And the objective probability of passing is p star. The agent doesn't know p star. Each period, the agent takes an action, either 0 or 1, and the utility is the action times y minus z. So you want to take the action if the probability of success is greater than z, if p star is greater than z. Well, what happens? So a lab experiment by Zimmerman finds that people are more likely to recall favorable tests. That leads them to overestimate their probability of passing. So people will end up taking action equals 1 when objectively they shouldn't, because they think they're better at this than they are. The agent acts as if they are misspecified about the true probability, and in particular, overconfident. And we'll see that this is an example of a selective memory equilibrium. So briefly on some related work, so this is not the first paper, even in economics, on selective memory. Sendel Mulanathan's job market paper was actually about selective memory. And then more recently, there's papers by Afruzi et al., Chu, Hoang, and Zhou, and Bordolo et al. And they differ from what we're doing, but they study the short-run implications of selective memory, so not the long run. So how does what happened today influence what happens tomorrow? Sendel looked at sort of correlations in actions over time induced by selective memory. Another branch of the literature that's related is the literature on endogenous misspecified learning, going back to Sponda and Puzo. So this is a literature where agents remember everything, but their prior rules out the true state of the world. They update like Bayesians, take actions, and they can end up doing the wrong things. And we're not studying misspecified agents here, but we're going to adapt some of the techniques from those papers. It turns out that some of the results about updating beliefs can be modified and ported over. And the last thing to mention is the literature on selective attention, which is related to selective memory, but it's different. Selective memory is you see everything, but you forget some of it. Selective attention, you maybe don't see some things in the first place. Okay, so Schwarzstein's job market paper was about that. Schweitzer and DeVries, it's not really not seeing them at all, but it's more you misweight them for exogenous reasons. Okay, so that's an overview. So I'm going to plunge into the formal details unless there's any questions. So each period t, starting in period 1, the agent observes a signal S from a finite set, capital S, and picks an action A, also from a finite set. And the pure strategy is then a map from signals to action. So for much of what we do, the signals aren't going to matter, but we have them in because there's this evidence that sort of the color of the room you're in can make you behave differently. If the light is blue, you remember things that happen when the light is blue and not when the light is red. So this lets us sweep in a number of empirical applications. Although it's, I guess, conceptually, theoretically, it's not doing much. So the signal and the action together induce an objective probability distribution P star over the possible outcomes, capital Y. And now this P star depends on both the action and potentially on the signal. And the agent's payoff, U, depends on the signal, the action, and the outcome. And for simplicity, we're going to assume the agent knows the distribution over signals. So we're not learning that. They're just trying to learn the conditional distribution over outcomes given a signal and action.
Are we to suppose that like signals are like states of the world, or?
Well, the signals are IID. So it's, if you think of state of the world as persistent, the state of the world is really this object P star, which is the true probability distribution, conditional action signals. So think of the signal is, well, in the case where it has no real effect on payoff, it's just the color of the light. Some days the light is green, some days the light is red, but it's IID. And so the agent knows this fixed and IID full support distribution over signals. So it's not really states. I mean, it's a very short run state of the world if you want. So I'm not sure what you meant by state of the world.
I think I understood, thanks.
All right. So agent has a prior mu naught over these probability distributions. It just doesn't know P star, but it knows that for every action and signal pair, there's some fixed probability distribution. They don't know what it is. So that's the set of things they're priors over. Okay, delta of Y to the A cross S. So implicit in this, the agent knows, believes and is correct that the map from actions and signals to distributions on Y depends only on the current action and current signal. So it does not depend on the action they took yesterday, does not depend on the signal yesterday. It's just the action today and signal today is what's going to drive today's outcome. They don't know the distribution on outcomes given A and S. They have this prior mu naught. Capital theta is the support of the prior. Is correctly specified if it's vector P star, where P star isn't a number, it's a vector, one probability distribution for each AS pair. So if P star is in set capital star is not in theta, the agent's misspecified. Maintained assumptions throughout the talk. The first one is that for every P the agent thinks is possible, all actions and signals, the objective probability of Y is positive if and only if the subjective probability of Y is positive. So this first part of the assumption has two implications. It says there's no data generating process the agent thinks is possible. No P in capital theta can be ruled out in finite time. And conversely, everything the agent thinks is possible has positive objective probability. And that's just for our convenience. It's not crucial. And the other thing I'm going to assume for the talk is that the agent is correctly specified. So that's just for convenience. By assuming that, it cuts down on some cases. And in fact, an early version of the paper did not require the agent to be correctly specified. So if you're curious what happens then, you can go look up the working paper version, an earlier working, because we haven't posted the new version. So the version on my webpage still has this. Okay, what is selective memory? So the agent's memory of past periods is distorted by a collection of signal-dependent memory functions. So M sum S prime says, I saw signal S prime today. What do I remember from the past? Well, for every past, we call them experience. Every triple, signal, action, and Y in the past, there's some probability M of remembering that observation. Okay. So this, give you a second to grapple with this. It's a little unusual. So the memory here is probabilistic. The agent at the same S prime, some days the agent might remember something and some days not. So it's not deterministic what you remember. And also memory selective. So this M function isn't a constant. I mean, if M was a half, no matter what, you'd be imperfect memory, but it would not be selective. Okay, and we're going to assert that both these features are well documented. The fact that memory, in fact, is stochastic and selective is in these psych/neuroscience papers by Kahana and Shadlin and Shahami. Okay.
So in the model, it seems that there is no time dependence. So will more recent memories be easier to recall?
No, not in this model. So you could imagine, extensions with some sort of recency bias. You're more likely to remember recent things. Have not done that. Good. So any other questions? That's a good question. And I'll point out, we'll come back to this later. So a consequence of this M, I mean, if M is positive, then, and the fact that you don't forget old things means eventually you're going to remember a whole lot of stuff. And you might question if people really have the ability to remember a whole lot of stuff. And so we're going to have an extension at the end where we bound people's memory. But here you can remember lots, just like the classic agent. It's just you don't, some things you don't remember. Okay. We assume that no matter what the current signal is, no matter what past signals and actions were, you remember something that happened. So you can't say, I've never, if you played action A, you can't say, I've never played action A. There's some AY, or you can say that. Sorry. If M was 0 for this A, you would never be able to remember having played action A. So you might unluckily not remember it, but we're going to make it possible to remember it. Okay. So history is just what you think it is, all the things that have happened up to T. The recalled periods, which periods do you happen to remember at time T? It's random. We have this function M, and at time T, we're going to look over all the past events, all the past SAYs, and say, probably M, you remember it, probably 1 minus M, you don't. That's going to be independent. Each past thing is remembered independently of whether the others are remembered or not. And if you remember something, you remember all of it. Exactly what happened that day. You could imagine the outcome Y is multidimensional. It's how hot it was, what the food tasted like, what color shirt you were wearing, whatever. And you might remember some components and not others. And so we do that in the appendix, but I won't be talking about it today. Okay, behavior. So, double comma, oh well. In the baseline model, so agents are going to be Bayesian. They're going to compute beliefs just like an ordinary Bayesian would. But with the one wrinkle, they think that the things that they remember is all that's happened. So this is, the agents are naive. We will discuss later on what happens if they're not naive or if they're partially naive. Yeah. But for now, the agents just, they forget stuff, but any given day, they form their beliefs as if what they remember is the only stuff that happened. A policy says what you do at every history. Okay. What kind of policies are we going to look at? Well, given the agent's belief mu and a signal, the agent can say, if this was my belief before I thought of a signal, now I'm going to compute the expected utility of A and Y. And I'll take whatever action maximizes today's expected payoff. So agents is myopic. So each day they take whatever action maximizes the expected payoff given their signal. Are we good? Okay.
I have a question, sorry, if I may.
Yeah.
So the payoffs are dependent on signal sections and the outcomes.
Yes.
And so is there any payoff consequence for correctly updating the objective probability? And so are there any assumptions on these distributions? Delta?
Not yet. We'll have some example. We'll have some different cases. So the consequences will be indirect. So it's not that someone comes and raps you on the knuckles for getting things wrong. It's more like in my leading example at the start, if you misremember all the times you failed the test, you will incorrectly infer you're really great at this, and you will do it too often.
Okay.
So that's a payoff consequence.
Okay, thanks.
Okay, so I mentioned this fact we assume the agents are naive. So partial naivete would be that for each Y, you might forget stuff, but the true probability you remember it is M, and you think you remember it with M hat. So the baseline model, M hat is 1. Agents think they remember everything. Okay. So we want to understand the agent's long-run behavior. So we have this object, KL, and it's called the memory-weighted KL minimizers. It's called that because the KL divergence pops up in the proof. But so I'm trying to convince the co-authors to change the name, because it's really, that's not what's important. And if you look at the definition of KL on the screen, it's not really the KL divergence. So minimizing the KL divergence is going to be the same as picking the p's that maximize the log likelihood of what you see. So we have this max of things. That's a kind of complicated expression with big parentheses, but let's ignore the sum over S. Okay. And let's ignore the M. If I make a second equation that cancels those out, that would be simpler. So if you do that, so if there's no signals, we can ignore psi of S. If M is identically 1, we can ignore that. And we're just maximizing P log P. So it's maximizing the log likelihood. So what's different here, there's two things. Well, there's different signals, different days. We have to take this weights over signals. That's pretty standard. But then some things, don't really get remembered very well. So we are maximizing this weighted sum because we're going to downweight the things you're less likely to remember. Okay. Is that clear?
Can you remind us what zeta is in this?
Sure, it's the
expression?
distribution over signals.
Thanks.
And it says it's probably easier to look at this without the signals. The general definition. Okay. Are people good on this? Is the key definition. This plus equilibrium. People good? Yeah, okay. So a strategy, which is a map from signals to actions, is a selective memory equilibrium if for every signal there's a belief nu sub S that's supported on the set KL. So this KL set needn't be a singleton. It might have 3 points. And then so any distribution on those 3 points is okay. So it has to be there's something you can believe that puts probability 1 on these KL minimizers or log likelihood maximizers that make what you're doing a best response. And the strategy is a uniformly strict selective equilibrium if no matter what belief you take over the set KL, you have a single optimal strategy. So sigma is the one unique best reply to your beliefs. Okay. Good. And a strategy is a limit strategy if there's an optimal policy where if the agent uses that policy, there's positive probability that we converge to that strategy. And the main theorem, every limit strategy is a selective memory equilibrium. So proof sketch, this proof by contradiction. Pick a sigma that's not selective memory equilibrium. Well, then there must be at least one signal after which it's not prescribing a best reply to these beliefs that put weight on the minimizers. We said, while the compactness and continuity shows this also holds for beliefs that aren't only exactly on the minimizers, but are near the minimizers. So if we can show beliefs, if you played sigma would concentrate on the minimizers, we're done. And Burke has a famous paper from the 60s on the convergence of misspecified beliefs when the agent faces an exogenous stream of signals. And we just extend that argument here. So it's a little different because the signals, what the agent's seeing depends on their actions, just as it does in misspecified learning. Okay, so that's the justification for the definition. Similarity weighted memory is a kind of selective memory where there's a metric on the signals. And the more the current signal is like the an old signal, the more likely you are to remember what happened. So this kind of selective memory does not depend on the action you took or the outcome. So that means that the true distribution is the best fit for every signal. So what these weights are has no effect on the long run minimizer. So this kind of similarity weighting has no effect on the long run outcomes. You're going to end up, if you're doing an action a long time, you will learn its consequences. And so selective memory equilibrium reduces to self-confirming equilibrium. Not to optimality, because you might have wrong beliefs about things you haven't done. Okay, ego boosting memory bias. Now, suppose there aren't any signals, and the outcomes reveal information about some ego relevant characteristic. Agent doesn't know the distribution of her outcomes, they're more likely to remember, agents more likely to remember situations that made them look good. So I think there's a typo in the slides here. The prior shouldn't be over delta of y, because you need a different delta of y for each action A. So that's a small typo. Suppose that M is constant in A and non-decreasing in Y, and utility is supermodular. So more able agents are the ones who should take higher actions. Okay, so let me talk some more about this Zimmerman experiment. The agent gets 3 noisy reports about their performance relative to other subjects, whether they're positive or negative. They have people take tests, and I said, you did better than the median or worse than the median, not if it's median or average. And if we assume the agent is more likely to recall favorable tests, so we can say that if you pass the test, you remember it with probability 1, and if you failed it, you remember it with some probability 5. If you did poorly, got a bad signal. So in the selective memory equilibrium, the agent overestimates their probability of passing. And so again, they behave as if they were misspecified and overconfident. So what's the advantage of this versus just assuming misspecification? Well, there is some psychology, neuroscience evidence for selective memory. That the misspecification is a convenient modeling tool that we like and have worked on, but it's hard to, people don't usually elicit priors, verify that agents are misspecified. That's a harder thing to get support for. Anywho, let's extend this to misattribution in joint task. Suppose the agent works in a group. So the outcome space is both the test result and whether the group project succeeded. And the distribution of Y2 depends both on this P1 star, how good the agent is, and some Q star, where alpha measures the correlation between performance of the two tasks. The agent knows this correlation. So the agent is going to see this outcome space each day. The distribution that matches the fraction of their own successes among the recalled experiences is an element of the prior, but it's a unique KL minimizer. But what is the perceived fraction of successes the agent has? Okay, well, there's a true probability P star. Every time they, that's the probability that they succeed, they remember that. And they remember all the successes, P star, but only a fraction phi of the failures. So that means that they think they are succeeding with probably P star plus this term that depends on phi. Now, the agent have this belief on their own ability, based on what they've remembered from that. They have to also, given the success of the group project, form a belief about a coworker's ability, about this Q star. And the agent, because the agent thinks they're better than they are, and they know the overall success probability, to make things add up, they think their partner is less good than they are. So they estimate the Q to be the true Q star minus a term. So the agent, is going to overestimate their own ability and underestimate their coworker's ability. Okay. Another application. Let Y be the money received by the agent, and the agent has some concave utility function, V of Y for money. There's a safe action with outcome Y naught, and there's a risky action A1. And suppose the agent remembers extreme events, so large and absolute value, or large, sorry, I misspoke. Extreme events are large departures from the expected value. So we look at Y minus the expected value of Y, and if Y is either much higher or much lower than that, that's striking. So you're more likely to remember that. Okay, well, that's going to make the agent's remembered distribution look much riskier than the true distribution. There'll be more weight on the tails. So if this true distribution is symmetric, and if choosing the risky action is not an equilibrium with perfect memory, so it's not optimal, then if we give you extreme experience bias, that pushes you towards the safe action. So if you didn't take the risky action before, you won't now, and it can go the other way. So it can shift you from taking the risky action to the safe action. Okay, let KL bar of capital theta be the minimizers with perfect memory. So in general, this set KL depended on the memory function, but memory function is identically 1. Then we'll say that a strategy is a Burke-Nash equilibrium if it's a best response to a belief over these exact KL minimizers with perfect memory. And a Burke-Nash equilibrium is a self-confirming equilibrium if there's a P in capital theta that exactly matches P star when sigma is played. Sigma is a uniformly strict Birch-Nash equilibrium if it's the unique best response. And the point of all this definitions is that with a sense in which selective memory equilibrium and Birch-Nash equilibrium are equivalent. They're not exactly equivalent. There's some subtleties and qualifications around the words uniformly strict. So I've got these things like here with this formal definition. That's a hyperlink. If people want to see formal definitions, I can always give more detail, but absent questions, I'll just go on. So every uniformly strict Birch-Nash equilibrium with some with some support theta, and now this needn't be a correctly specified theta, is belief equivalent to a selective memory equilibrium with full support for some memory function. And conversely, every uniformly strict selective memory equilibrium with some particular support capital theta is belief equivalent to a uniformly strict Birch-Nash for possibly some other prior capital theta prime.
Excuse me, did you say something about existence of equilibria?
Good. We, yes, good. That's very good. I am pretty sure they exist, but I'm trying to remember if we state that in the paper. No, hold on. No, let me stop and think. Good. So we don't have access to sort of the obvious one way to try to prove existence of these equilibria would be to say, well, beliefs converge, and anything they converge to is an equilibrium. So we don't have access to that because we don't have a convergence theorem. The theorem 1 said if beliefs converge, that it is an equilibrium. The same thing was true in our selective memory paper, and there we used a sort of min-max argument to give a direct proof of existence of equilibria, but the equilibria may need to be mixed. So we have defined equilibria here to be pure, and I think there's no hope of having existence in pure equilibria here, for the same reason that there's no existence of pure, there's not guaranteed. Giacomo, okay, thanks Giacomo. Giacomo is here in the online. He just sent me a chat message. Yes, if the prior is full support, we have existence. Okay, so that's interesting, Giacomo. Of pure selective memory equilibrium or of mixed selective memory equilibrium? Giacomo, of pure, really? Okay, so I did not. Thanks, Jerome. I haven't given this paper for a while. I'd actually forgotten that. Well, since Giacomo's answering my questions, I'll ask him one more. Do we actually mention this in the paper somewhere?
Let me try to unmute myself. Can you hear me well?
Oh, yeah.
Okay, yes, sorry, because yes, we have in an appendix a proof that if the agent has full support beliefs, then the equilibrium always exists. Now, you can obtain the existence in even under a weaker condition, that is that the memory distorted outcome distribution belongs to the support. That is something that is obviously guaranteed by having a full support. In general, the interplay of misspecification and selective memory equilibrium can induce failure of existence. If you're willing to allow for mixed, we have existence throughout. But that's not something that we do in the paper. So we don't consider equilibrium.
Good. That's good. So when we first wrote the paper, we allowed the agents to be misspecified as well as to have selective memory. So then there was no hope of existence of pure. But we've now restricted to correctly specified. Okay, but which is still not full support, but okay. Well, great. So I learned something. This is good. Thank you, Jerome.
You're welcome. So even for the strict version, they exist.
Giacomo? I doubt
Even
that.
for, sorry, even for the,
For
What's the existence of
version,
strict?
there were two definitions in the first.
Well, there's not. There's a definition of equilibrium and of uniformly strict. No reason to have uniformly strict.
no reason to have uniformly strict, because the problem may be trivial in which you have indifference for all beliefs, and so strictness is the, so you need to put more structure to have uniform strictness, definitely. You at first to rule out trivial case, but even more than just trivial case.
Okay, thank you.
Welcome.
Okay, and this uniform strictness is needed. There are Burke-Nash equilibria that aren't equivalent to any selective equilibria of full support, and selective memory equilibrium that aren't belief equivalent to Burke-Nash. Unlike Burke-Nash, selective memory equilibria don't reduce to self-confirming with correct specification. Okay. Behavioral implications. Misspecified learning has been proposed as an explanation for persistent suboptimal behavior, like overconfidence in Heidisch-Kosegi-Strack, incorrect beliefs in Lemon's markets, Esponda, and failure to understand regression to the mean, Esponda and Puzo. But some analysts question why the agent doesn't realize they're misspecified once they have lots of data. Lots and lots of data, you might worry about this. In fact, this is what Giacomo's job market paper makes him one of those analysts who might question it, because he has agents who question their misspecification with data. Our result shows that every behavior that can be rationalized as misspecification can also be rationalized by selective memory. Well, yeah, leaving off the uniformly strict words. Illustration, consider a buyer who submits an offer for a good in a double-blind two-sided auction where price is the buyer's bid. So the seller's dominant strategy is bid their value. And after every interaction, the buyer observes their payoff in the ask price. So a correctly specified agent with perfect memory would learn the optimal bid. If the buyer dogmatically believes that the price seller's ask is independent of the quality of the good they're selling, then their Burke-Nash equilibrium, it's the misspecified agent who thinks that the quality is independent of price, then they won't learn that if they offer a higher price, they get higher quality. So we can have Burke-Nash equilibrium where the price is too low. Memory distortions that overweight experiences with the large gap between values and ask prices can lead the agent to believe that value and bid are independent and have the same behavior and beliefs as misspecified prior. So this is just an example of how we can take a observation about persistent misbidding that was explained with misspecification and explain it with selective memory. Old paper by Phillips and Edwards has a different kind of memory error. So it's not stochastic memory, it's deterministic. It's not even memory error. This is agents who use the wrong likelihood function. So with under inference, you apply Bayes' rule, but instead of having the true probability of an action, you have it to some power m, less than 1. And in terms of long-run behavior, these things are equivalent. If sigma is a limit strategy with under inference distortion m, it's a selective memory equilibrium with memory function m. So a corollary of that is that if m is a constant, then correct specification has no long-run effect. So that raises the question, and it was a question about look at the evidence for under inference surveyed in Benjamin. Can we tell if it's under inference or selective memory? The answer is we don't think so. We need more experiments about what people actually remember to distinguish using the wrong likelihood function from not remembering some things. Okay, so the baseline model, the number of recalled experiences goes to infinity as the sample size increases. This is, I said that in response to an early question. So suppose that we want the expected number of things you remember to be bounded. Let's drop the signals. And now let's let the probability of remembering a time t, decrease at rate 1 over t. Okay. So now there'll be some finite expected number of things you'll remember. So this is, I think, well motivated. It's substantially more complicated because now, if the agent is, when the agent had an infinite memory, eventually you could hope beliefs settle down, actions settle down. If on average you remember 4 things, then which 4 things you remember are going to matter. So your beliefs are stochastic, so your actions are stochastic. So instead of looking at convergence to an action, we're going to look at convergence of the empirical action frequency. How often did you play each action? So let eta super m, the memory function, sub alpha, be a distribution over histories where the number of times a given action outcome pair appears has a Poisson distribution. And the intensity parameter of this Poisson depends on how often you're playing action A, the probability of outcome Y under A, and the probability that you remember the pair AY. Okay, so that's a complicated formula for this that I didn't even attempt to hyperlink for. But hopefully people have the basic idea. I think it's pretty intuitive. But how often you have a distribution over histories, how often you remember something? Well, if you played it a lot, you more likely remember it. And if you remember it a lot, you're more likely to remember it. Okay. So if we had a fixed alpha that was played forever, there'd be some corresponding distribution of beliefs. It wouldn't be a fixed belief, there'd be some distribution of beliefs. A stochastic memory equilibrium is a mixed strategy alpha. So there's a Markovian policy where at every belief mu, the action is optimal. And alpha is the action frequencies induced by rho. So how often you play action A, according to alpha, is how often, if you played alpha all the time, how often would your beliefs make playing A optimal? So I think it's a very natural generalization of selective memory equilibrium to a case of stochastic beliefs. And we have the natural extension of the result. If alpha t goes to alpha with positive probability, then it's a stochastic memory equilibrium. So it's good. As I said, it's clear from the definition, the limit frequency is a fixed point. The distribution of actions, the best reply to a distribution of beliefs that action distribution would generate. Okay. Yet more complicated extension. Again, it's, as we get more and more motivated, life gets harder and harder. And this is a bit related to this question about you remember recent things more. This is a step in that direction. We'll say that if you remember something yesterday, you're more likely to remember it today. So now, given what's happened in the past, the sequences of actions and outcomes, what you remember is no longer conditionally independent because it depends on what you remembered yesterday. So there'll be a sequence, there'll be a collection of distributions of what you're going to remember, but depend on what you remembered yesterday. And we showed that every action alpha induces a Markov chain over the recalled histories that has a unique invariant distribution. And we then show this distribution converges. Okay, so it's so conceptually the same. And we have you conditioning on yesterday's realized history. given this structure of argument, if we let you condition of the last two things you remember, that would probably work also. I mean, we'd like to keep it finite, the number of past things you recall. Okay. Good. And I guess I took everything but the proof out of this. Well, yes. Good. We did that. So I mentioned partial naivete. Since I have, Eric, should I plan on talking until the hour, or what's your pleasure on the timing? I could stop now, or I could go on.
You can continue. I mean, we had some discussion during the talk, so continue a bit, and then we'll have a little bit of discussion at the end.
Perfect. So, you know, I talked about this case where agents remember the occurrence of y with m of y, but they think they remember it with probably m hat. Well, see, what's complicated now is that the agent is only partially naive. They know they forget things. So they have to think about what they might have forgotten. So now the set of minimizers depends both on your true memory function m and what you think your memory function is m hat. And the distributions your beliefs will converge to will be things that maximize the sum. So we have the probability that you remember y, m of y, times p star of y, times log of m hat of p of y. Remember, the baseline model, m hat equals 1. So we had m p log p. But also, now the probability you remember nothing. Well, the objective probability you remember, sorry, the probability you think you remember nothing is, you know, use m of y. So 1 minus m of y p star is the probability that you don't remember something. And 1 minus m hat, 1 minus the sum of m hat p of y is how likely you think you won't remember something. Yes, so again, so in the baseline model, m hat equals 1. So if you think you remember everything, this subjective probability that nothing recalled term on the lower right is 0, because the sum of p of y is 1. So partially naive selective memory equilibrium is you play a best response to these new KL objects. So if you know you forget things, but you don't think your memory's selective, so you think you just forget some things at random, it's the same as if you're fully naive. If you're fully aware of your memory function, then selective memory equilibrium coincides with Burke-Nash equilibrium. And in our setting that we now have of correctly specified agents, that means they coincide with self-confirming equilibrium. If the agent partially realizes the memory selective, the relevant measure of distortion is m over m hat, the ratio between how forgetful they are and how forgetful they think they are. Okay, if the agent is partially naive, every limit strategy is a partially naive selective memory equilibrium. It's not surprising given all of this. So conclusion, selective memory equilibrium characterizes the long-run implications of forgetful agents. Extensions, it could be fun. We have these IID signals. We could have Markov signals. And the reason for doing that, if the agent thought the signals were Markov, that would let them do screwy things like believe in the gambler's fallacy. The coin has been heads 3 times, then they have to expect it to switch to tails. If they mostly remember switching and not persistence. We could allow memory to depend on the frequency of experiences. So the first time something happens, it might be more memorable than the 6th time. We haven't done any of those. I think there's lots of things that one could do. We sort of, the front half of the paper, we went for the model that made things as simple as possible and gave us some results. And then, we have these extensions to the finite memory. That was the one real extension direction that we've worked on so far. Okay, so thank you very much, and thank you for the questions. Very helpful. Happy to stick around and take more questions if there are any.
I have one.
Please.